Hello everyone. In the beginning of the class, let us see new announcements. Okay, the first new announcement is May 10th, 2022. Class videos uploaded. Hello everyone. I have uploaded class videos of May 10th, 2022 to YouTube. Their URLs are this, and this. Best regards, Wei Zhen. Okay, the second new announcement is the handout of Chapter 2 has been updated. Version 2022-0512. Hello everyone, I have uploaded the latest version of the handout of Chapter 2 to eCourse2 website. The location and the file name are eCourse2 website, wireless communications and machine learning, course content, handouts, Chapter 2 handout 2022-0512.pdf. Best regards, Wei Zhen. Okay, next let us see the progress of the last class. Okay, in the last class we have taught to Chapter 2 handout, page 47, problem 35, solution, equation 45, finished. Okay, please open the excuse me. Okay, please open the handout of Chapter 2 and you can search for equation 45. Okay, like this. Okay, so we are talking about, okay, let us review what we are talking about. Okay, we are talking about problem 35. What is gradient descent? Okay, so we have a monotonic sequence f of x0, which is greater than or equal to f of x1, which is greater than or equal to f of x2, which is greater than or equal to etc. Okay. So where x0, x1, x2 is a sequence such that equation 44 is established. Okay, that is xn plus 1 is equal to xn minus gamma n times the gradient of f of xn, where n is greater than or equal to 0. Okay, what is gamma n? Okay, gamma n is the learning rate, okay, at the nth iteration. And what is capital F? Okay, let us see what is capital F. Oh, not here. Excuse me. Okay, so capital F is a multivariable function. Okay, f of x is defined and differentiable in a neighborhood of a point A. Okay. Okay, so hopefully the sequence xn converges to the desired local minima. Okay, note that the value of the step size gamma is allowed to change at every iteration. Okay, so I wrote gamma n in equation 44. Okay, this means that for the different iteration n, Okay, gamma n can be different. Okay, with certain assumptions on the function f, for example, f convex and the gradient of f is Lipschitz. Okay, what is excuse me. Okay, what is Lipschitz? Okay, we will explain it later. And particular choices of gamma. For example, chosen either via a line search. Okay, what is a line search? We will introduce it later. That satisfies the Wolf conditions, or the Barzilai-Borwin method shown as following. Okay, so gamma n is equal to the absolute value of xn minus xn minus 1 transpose times the gradient of f at xn minus the gradient of f at xn minus 1. Okay, and divided by the square of the norm of the gradient of f at xn minus the gradient of f at xn minus 1. Okay. Okay, so converge to a local minima can be guaranteed. When the function f is convex, all local minima are also global minima. Okay, it is a very important property of a convex function. Okay, all local minima of a convex function are also the global minima of the convex function f. Okay, so in this case, gradient descent can converge to the global solution. Okay, this process is illustrated in figure 28. Okay, let us see figure 28. Okay, figure 28 is the illustration of gradient descent on a series of level sets. Okay, we will introduce what is a level set later. Okay, please look at this figure. Oh, I need to make it smaller. Okay, so let me try. Okay, first 100%. Okay, this is too small. Okay, so I think I can use 200%. Okay, 200%. Oh, okay, good. So this is the level set of a function, and we want to find the minima of the function, which is here. Okay. So the level set of its function is represented by these blue curves. Okay. So x0 is the initial point. Okay. Then we find the direction of the negative gradient, which is the red arrow. Okay. And then we arrive the point x1. And at the point x1, we also find the negative gradient, okay, which is the red arrow, and then we reach x2 and so on, and it is point to x3 and x4. Okay, finally we will approach the minima here. Okay, let us go back to the first figure 28. Okay, here. Excuse me. Okay, here f is assumed to be defined on the plane, and that its graph has a bowl shape. The blue curves are the contour lines. Okay, that is the regions on which the value of f is constant. Okay, a red arrow originating at a point shows the direction of the negative gradient at that point. Note that the negative gradient at a point is orthogonal to the contour line going through that point. Okay, let us see figure 28 again. Okay. So in this figure, we can see that we start at x0, and this red arrow is the negative gradient. And you can see that it is orthogonal to the contour line at this point. Okay, similarly at x1, this arrow, okay, is orthogonal to the contour line. Okay, this line, okay, at x1. And so on. Okay, x2, x3, x4, okay, etc. Okay, let us go back to here. Okay, we see that gradient descent leads us to the bottom of the bowl. That is, to the point where the value of the function f is minimal. Okay, then let us see problem 36. What is Lipschitz? Okay, solution. Given two matrix spaces. Okay, what is a matrix space? Okay, you can click on it. I have put a hyperlink, and you can see that we will go to problem 31. What is a matrix space? And we have already introduced it. If you forget what is a matrix space, please see the solution below. Okay, let us go to the matrix space we have just mentioned. Okay, matrix space. Oh, cannot find. Okay, that is okay. Okay, please go to, if I remember correctly, problem 36. Okay, good. So, given two matrix spaces x dx and y dy, where dy denotes the metric. Okay, what is the metric? Okay, you can see that here is a red box here. Okay, it is a hyperlink. So you can click on it, and we will go to problem 32. What is a metric? So we have already introduced what is a metric. If you forget, please review the solution to problem 32. Okay, let us go back to problem 36. Okay. Excuse me. Okay, where dy denotes the metric on the set x and dy is the metric on set y, a function f x to y. Okay, do you know what is the meaning of f colon x to y? Okay, it means that f is a function and x is the domain of f, the function f, and y is the range of the function f. Okay, so a function f(x to y) is called Lipschitz continuous if there exists a real constant k which is greater than or equal to 0. Okay, such that for all small x1 and small x2 in capital X, dy of f of x1, f of x2 is smaller than or equal to k times dx of small x1, small x2. Okay, next let us see problem 37. What is line search? Okay, why do we need to know what is line search? Okay, let us search, line search. Okay, the previous, next. Okay, so line search appears in the solution to, okay, the previous one. Okay, appears in the solution to problem 35. What is gradient descent? Okay, and why do we need to know what is gradient descent? Okay, let us search for the gradient descent. Okay, and the previous. Okay, previous. Okay, because the term gradient descent appears in the solution to problem 2. What is stochastic gradient descent? Okay, and why do we need to know what is stochastic gradient descent? Okay, because let us open the slides of chapter 2. Excuse me. Okay, and please go to page 47. Okay, because on page 47 of the chapter 2 of the slides, stochastic gradient descent method, okay, we have mentioned it, so we need to explain it. Okay, let us go back to the handout and go back to, okay, if I remember correctly, problem 37. Okay, good. Okay, problem 37. What is line search? Solution: in optimization, the line search strategy is one of two basic iterative approaches to find a local minimum x star of an objective function f. Okay, f is a function from r to the power of n to r. Okay, do you remember what does this symbol mean? Okay, it means the n-dimensional real vector space. Okay, and R is the set which contains all real numbers. The other approach is trust region. Okay, we will introduce what is trust region later. Okay, the line search approach first finds a descent direction along which the objective function f will be reduced, and then computes a step size that determines how far x should move along that direction. The descent direction can be computed by various methods, such as gradient descent. Okay, gradient descent. Okay, we have introduced what is gradient descent in problem 35. Okay, if you forget, please review the solution to problem 35. Okay, let us go back to problem 37. Okay. Or quasi-Newton method. Okay, we will introduce what is quasi-Newton method later. The step size can be determined either exactly or inexactly. Okay. Example use. Here is an example gradient method that uses a line search in step 4. Okay, the first step, set iteration counter k be equal to 0 and make an initial guess x0 for the minima. Okay, step 2, repeat step 3 to step 6. Then step 3, compute a descent direction pk. Step 4, choose alpha k to loosely minimize. H of alpha is equal to f of xk plus alpha times pk over alpha. Alpha is in the set R plus. Okay, what is R plus? It is the set which contains all the positive real numbers. Step 5, update xk plus 1, which is equal to xk plus alpha k times pk, and k is equal to k plus 1. Okay, step 6, until the norm of the gradient of f of xk plus 1 is smaller than tolerance. Okay, at the line search step 4, okay, this step, step 4, okay, the algorithm might either exactly minimize h by solving h prime of alpha k is equal to 0. Okay, h prime of alpha k is the derivative of the function h at alpha k, or loosely by asking for a sufficient decrease in h. One example of the former is conjugate gradient method. Okay, we will introduce what is conjugate gradient method later. The latter is called inexact line search and may be performed in a number of ways. Excuse me. Such as a backtracking line search or using the Wolf conditions. Like other optimization methods, line search may be combined with simulated annealing to allow it to jump over some local minima. Okay. So next, let us look at problem 38. What is the trust region? Okay. Solution: because of time limitation, I do not plan to introduce it here. Okay. If I explain all the proper nouns here, I think we will always stop on page 47 of the slides of chapter 2. So we must move forward. Okay, problem 39. What is the quasi-Newton method? Okay, solution: because of time limitation, I do not plan to introduce it here. Okay, problem 40. What is the conjugate gradient method? Solution: because of time limitation, I do not plan to introduce it here. Okay, problem 41. What is the backtracking line search? Solution: because of time limitation, I do not plan to introduce it here. Okay. Okay, problem 42. What are Wolf conditions? Okay, again, solution: because of time limitation, I do not plan to introduce it here. Okay, problem 43. What is the simulated annealing? Okay, solution, because of time. Okay, it is 25 minutes. Let us take a break.